In section 1.6, we'll talk about counting meaningful numbers, or significant digits, to communicate the precision of a measurement or calculated result. There are a lot of learning outcomes to get through for significant figures, so pause the video here, if needed, to take notes. We'll also talk briefly about precision and accuracy. Let's begin. When we make measurements in science, they fall broadly under two categories. If we're trying to describe what something is, we're using qualitative descriptions. If we're describing how much of something is present, we're making quantitative measurements. Scientific measurements are usually repeated 3 or more times because the average value of the measurements is probably closer to the true value than any individual measurement. The accuracy of those measurements describes how close the average is to the true value, such as the bullseye on a dartboard. The precision describes the closeness of all measured values to one another. Looking at the first dartboard, the measurements are not accurate because they fall far from the true value in the middle, but they are precise because the darts are all close to one another. The middle dartboard shows a result that is both accurate, the darts are all on the bullseye, and precise. The results are clustered close together. The dartboard on the far right shows a result that is not accurate. The average position of the darts is not in the middle, and the measurements themselves are scattered everywhere, showing a low degree of precision. Let's try a more concrete example. Suppose a bathroom scale registers 2 pounds without a load. An object is weighed repeatedly on this bathroom scale, and each results in a reading of 117 pounds. Are the measurements precise? The repeated measurements are identical, so yes, the measurements are precise. Are the measurements accurate? No, the measuring device was not zeroed properly, so it's falling away from the true value. What is the probable true weight of the object? Probably 115 pounds, accounting for the 2 pounds before we put anything on it. We've discussed the precision associated with making multiple measurements, but what about the precision involved in making a single measurement? There will be variation in making the measurement due to the instrument being used. Have you ever used a ruler with really thick divisions? How do you know how precise your measurement is? To answer that, we'll try a couple of examples, keeping in mind that we will always estimate one digit beyond the smallest scale division on the tool we're using to make the measurement. If we measure this shell using the bottom centimeter markings, we can see the true value of the shell's width lies somewhere between 4 and 5 centimeters. We can say with certainty that it is 4 centimeters wide, but then we need to estimate one additional digit. I'd say that 4.1 is a reasonable result. If we move to the top markings on the ruler, though, we go from centimeter divisions to tenths of a centimeter, or millimeters. In this case, we can measure with certainty that the shell is between 4.0 and 4.1 centimeters. We need to estimate an additional digit, and since it doesn't quite reach the 0.1 centimeter mark, we could reasonably estimate the width of this shell as 4.09 or 4.08 centimeters. Here's one for you to try. What is the length of this screw, not including the head, which has been purposefully left off the scale? Hopefully you estimated something close to 1.75 centimeters. We have markings to the tenth of a centimeter, so we must estimate the additional digit. As you've just seen, scientists report the precision of their measurements every time they write down a result, since they record all the numbers they know with certainty, plus an additional estimated digit. These recorded digits reflect the precision of the measurement, so we call them significant digits or significant figures. In order to preserve the appropriate amount of precision in our measurements as we manipulate them mathematically, there are several rules to follow. All non-zero numbers in a properly reported measurement are significant. Any zeros to the left of all non-zero digits are not significant. 0.03 contains only one significant digit. Any zeros between significant digits are significant. 903 contains 3 significant digits. Any zeros to the right of all non-zero digits in a number with decimal place digits are significant. 70.00 contains 4 significant digits. This indicates how precisely we were able to make this measurement. Any zeros to the right of all non-zero digits in an integer, such as in 4,000, are uncertain unless further information is given. 4,000 has only one significant digit. All the digits in the coefficient of a number in scientific notation are significant. Let's practice these rules to make sure we understand them. Which of the digits are significant in the following measurements? Pause the video to work through each of these. If you didn't get the correct answers, go back to the rules on the previous slide to troubleshoot. Calculated answers must be rounded to the correct number of significant digits, and we have a rule for handling addition and subtraction. For example, if we're adding 6.2 centimeters to 9.203 centimeters, we cannot report an answer that is more precise than our least precise measurement. The easiest way to accomplish this is to line the numbers up, perform the calculation, then round to the least precise digit. Let's try an example. Calculate the sum of 10.10 centimeters plus 1.332 centimeters plus 6.4 centimeters. Report the answer with the correct number of significant digits. Of the values added, 6.4 only has one decimal place, so the final answer is rounded to one decimal place. For multiplication and division, the number of significant digits in the measurement with the fewest significant digits limits the number of significant digits in the answer. So let me try that again in plain English. If we're multiplying 4.1 by 21.07, 4.1 only has 2 significant digits, so our answer can only have 2 significant digits. We say the answer is rounded to the fewest number of significant figures that are present in the multiplied or divided values. Let's try some examples. Can you report the results to the correct number of significant digits? The first answer is limited to 3 significant digits, so we round to 9.12. The second answer is limited to 2 significant digits by the value 4.9 grams. While counting significant figures, or sig figs as we often call them, we need to recognize that exact numbers are not used to determine how many digits to report. Exact numbers include numbers that are definitions, such as the 32 in the temperature conversion formula going from Fahrenheit to Celsius. Counted items are exact numbers, and integers and formulas are exact numbers. Let's try an example. The radius of a circle is 13.7 centimeters. Calculate the diameter of the circle to the correct number of significant digits, knowing the diameter is equal to twice the radius. Did you get a diameter of 27.4 centimeters? Here, the number 2 does not limit our significant figures because it's considered an exact number. All right, let's apply what we know to some mixed operations. Recall the correct order of operations, PEMDAS, taking care to keep track of the correct number of significant figures after each step in the calculation. In the first problem, we multiply 92.12 by 0.912, which limits the results, 84.01, to 3 significant figures. We'll carry all 4 digits through the calculations, however, to prevent a round-off error. Next, we add 84.01 to 233.02. We get 307.03, but we know this is only significant down to the 0 in 84.01, so we round to the tenths place, reporting 307.0 grams as our final result. The second calculation is a little easier. We take the difference of 80.21 grams and 79.93 grams to get 0.28 grams as a result. Both measurements were precise to the hundredth place, so 0.28 has two significant figures. When we divide that by 65.22, which has 4 sig figs, we must round the result to 2 significant digits. I'm only going to briefly touch on the rules for logs and anti-logs here because you won't really use this until Gen Chem 2. When you take the logarithm of a number, the log is essentially a function that goes out, finds the exponent on the number, and reports that back. So the log of 3.5 times 10 to the 5th would report back the exponent 5. This 5 goes to the left of the decimal, then the significant figures go to the right of the decimal. Anti-logs work the same way. The number to the left of the decimal is reporting the order of magnitude, or how many times the decimal point has been moved to get the original number into scientific notation. So the 3 here is not significant, but the numbers after the decimal point are, so the anti-log of negative 3.421 needs 3 significant figures when you're reporting it. That's all for this lecture. I'd encourage you to watch all the videos and work all the practice problems in the textbook to get comfortable with these rules. If you're having any difficulties, please post those questions to Piazza so that everyone can benefit from the discussion.